Hi everybody, this is 𝗦𝘁𝗆 𝗖𝗍, and in this video I'll be discussing the next question of Codechef's April long challenge, which is the strange number. So I'll be reading the question out first and then I'll be discussing its solution. You can open the link for yourself and read it if you want to, and I'll anyway be reading the question. So let's start. The first paragraph is just a story. The actual question starts from here. The guard gave 𝗏 two integers x and k. We want to determine whether there is an integer a such that it has exactly x positive integer divisors and exactly k of them are prime numbers. Okay, she found the problem to really hard to solve. We have to help her. Okay, the input format is that the first line contains t, which is the number of test cases. Then each test case consists of only one line, and the line consists of two integers, which is x and k. So once again, we need to find if there exists an integer with exactly k number of divisors, sorry, with exactly x number of divisors and exactly k number of positive prime divisors, right? So there are two subtasks, which is in the first subtask the number of test cases are smaller and the k value can be just 1 or 2, and the second subtask's constraints are given here. So this point onwards I'll be discussing the solution. You can pause the video, think it around for yourself if you want to. I'll just first discuss this smaller test case. Now if we know that k is less than or equals to 2, let's say we get a value of k to be 1, right? If the value of k is 1, it means that the number a is exactly having one prime divisor, which is it is of the form p. The a number itself is a prime number, right? It means that if the number is p, it means it is p raised to power 1, right? And if that's the case, we can be sure that the number of total divisors it is going to have can only be 2, which is 1 and a itself, right? So in this case, if k equals to 1, x must be 2. If x is not equals to 2, our answer is no, otherwise it's yes. For the case k equals to 2, a is going to be of the form p1 raised to power alpha 1 and p2 raised to power alpha 2, right? p1 and p2 are prime numbers here, and alpha 1 and alpha 2 are the powers of these prime numbers. Now these alpha 1 and alpha 2 are greater than or equal to 1 for sure, right? Because if they are 0, it means that that prime number wasn't actually a divisor of a, right? Now if you see, in this case the number of divisors are going to be alpha 1 plus 1 into alpha 2 plus 1. This is because while choosing a while choosing a divisor, the power of p1 that is included in that divisor can be from 0 to alpha 1. So we have alpha 1 plus 1 options for choosing the power for p1, and the number of ways of choosing the power for p2 is similarly 0 to alpha 2, which is alpha 2 plus 1. So the total number of ways are going to be alpha 1 plus 1 into alpha 2 plus 1. Now this should be equal to x, right? Because it tells that the number of total divisors that it has should be x. And if we know that alpha 1 and alpha 2 are greater than or equal to 1, and we can obviously assign any number to the alpha 1 and alpha 2, it is in our hand because the number a has to be chosen by us only. Then alpha 1 plus 1 is greater than or equal to 2, and alpha 2 plus 1 is also greater than or equal to 2. Now we just need to check that is it possible for x to be written as a product of two numbers that are greater than or equal to 2, right? If that's possible, it means that we would be able to come up with such alpha 1 and alpha 2's that their product is x. And if we are able to come up with such alpha 1 and alpha 2's, it means that we can choose the value of a accordingly, and we have an answer, right? Now if we are able to write x as a product of two numbers that are greater than or equal to 2, it means that x is a composite number, right? Because no prime number can be written as a product of two numbers that are greater than or equal to 2, and every composite number can be written as a product of two numbers that are greater than or equal to 2, right? Because these are the definitions of the composite and prime numbers, right? Now for the which means that for the case k equals to 2, we just need to check if x is composite or not. X is composite or not. It means that for k equal to 2, if x is composite, our answer is yes. If it's prime, then our answer is no. And checking composite and prime can be done in big of root x, and x is up to 10 raised to power 9, so this is not going to be a problem. Now let's discuss the more general case in which k can also up to be can be also up to 10 raised to power 9. When we are considering the more general case, we know that exactly k prime factors, right? A has exactly k prime factors, right? Let's say that the prime factors are p1, p2 and pk. Okay, now we can write a as p1 raised to power alpha 1, p2 raised to power alpha 2, and so on up to pk raised to power alpha k, right? The alpha 1, alpha 2, alpha k are basically the powers of the primes, and these are k different prime numbers, right? Now, as we just discussed in the case where k was equals to 2, similarly in this case, the total number of divisors of this number a are going to be alpha 1 plus 1 into alpha 2 plus 1, and so on up to alpha k plus 1. In other terms, it's pi I equals to 1 to k alpha I plus 1, right? Now we want this to be equal to x, right? We want this product to be equal to x, and we know that each of these values are greater than or equal to 2, and that's the only constraint these values have, as we can choose the value of alpha 1, alpha 2, alpha k by ourselves, and the value of a will be chosen accordingly, right? So again, we basically need to check that is it possible to write x as product of exactly k numbers, let's say ni, such that for all I, ni is greater than or equals to 2, right? This is the only constraint that we have. Ni should be greater than or equals to 2, and it should be written. It should be possible to write x as a product of exactly k such numbers, right? Now to check it, let's analyze the prime factorization of x itself, because that will give us an idea of how many that will give us an idea about x can be written as a product of how many different numbers. Let's say the prime factorization of x is p1 dash raised to power alpha 1 dash, p2 dash raised to power alpha 2 dash, and so on up to p of k dash dash to alpha k dash dash, right? Or simply let's use the variables r and beta, r1 beta 1, r2 beta 2, up to r say z alpha beta z, right? Let's say this was the prime factorization of x. Now if we see this itself, these numbers itself have a product of x, right? And these are z different numbers. We have assumed that number of different prime factors of x are z different numbers, right? Now let's try to basically like before trying to do what I am trying to do, let's try to see if we can reduce this number of numbers. To do that, we can simply combine one or two numbers into a single one. Let's say if we have written alpha equals to x equals to n1 into n2 into n3, we can simply reduce the number of numbers that are written on the right side by combining two or more numbers. To reduce these numbers, we can simply say that x equals to n1 into n2 into n3, right? Now what I was basically trying to tell you here is that what we'll do is we'll find the maximum maximum count. Let's say c, such that x can be written as a product of c different numbers ni, where each ni is greater than or equals to 2, right? If this count c is greater than or equal to k, it means it can be written as a product of exactly k numbers, right? Because if c is equals to k, then well and good. If c is greater than k, what we can do is we can basically combine several numbers into one, so that we get the count to be exactly k, right? Now how do we find this maximum count? We'll try and split these prime numbers into different numbers, because we know that the product of these prime numbers is the product of this r1 power beta 1 and r2 power beta 2 and so on is exactly x. What we can do here is that we can split these numbers into different numbers. What we can do is we can write these all of these r1s, these primes, differently. R1 into r2, sorry, r1 into r1 beta 1 times into r2 beta 2 times and so on up to rz. This will be beta z times, right? Now if I have splitted the numbers in this way, it is not possible to split them further, because each number is a prime number itself, and we cannot get two numbers that are greater than or equal to 2 and have a product equal to that particular number, right? Now the number of numbers that are written over here is simply the sum of the powers of the prime factors of x, right? Sum of the powers of the prime factors of x. Now if the sum of the prime factors of x is greater than or equal to k, that is the c is greater than or equal to k, then our answer is yes, else our answer is no, right? uh, because if c because we know that c is equal to the sum of powers of the prime factors, and we already discussed that if this c value, the maximum count such that x can be written as pi 1 to I equals to 1 to c and I is greater than or equal to k, we can reduce the count to k by combining multiple numbers. If it is less than k, then we cannot simply increase the count further, because each number uh, out of those c numbers would be itself prime, and it wouldn't be possible to split them further, right? So I have implemented the code already. It's a pretty simple one. uh, the first line is the number of test cases, 1 in this case, then x and k, 4 and 2 in this case. Then I'll initialize my count, which is c value, by 0. Then I'll iterate from starting from I equals to 2, and will iterate till I into y is less than or equals to x. And then while x is divisible by I, I'll increase my counter and I'll keep dividing the x value by I. When dividing this x value by I am ensuring that I am only counting the powers of prime factors in this loop, and not the uh, you know the composite numbers. For example, if x was say equals to 10, and when I equals to 2, I would have incremented by my counter by 1, which is count equals to 1, and x would have become 5, right? Now let's take a bigger example. Let's say it was 100 and x equals to 50, right? uh, and again 50 is divisible by 2, then count would have become 2, and x equals to 25. Now in case of 3, it won't be divisible, 25 won't be divisible by 3. Now when I reach I equals to 4, now this although the original number was divisible by 4, but this current value of x won't be divisible by 4, because I have already eliminated all the powers of 2, which means that when I visit any multiple of 2, it won't be counted again, right? So in this case I'll count all of the prime factors powers, and in the end I'll simply see if x is still greater than 1. If it is the case, it will be the case in case of let's take an example, 2 into 9, 2 into 11. Okay, in this case, when I'll iterate till root x, then also I'll have 11 left as my prime, so I'll simply do count plus plus if x is greater than 1. It is a pretty simple way. If I am if I made a some if I was unclear while explaining, you can search it on the net that how to find the prime factorization of a number. You will get it. Now I'll simply check if the count is greater than or equal to k. If yes, I'll print yes, that is 1, or else I'll print 0. I hope the solution code is clear. I hope that the intuition behind the solution is clear, and we see that the time complexity of our code for one test case is big of root x, right? Big of root x means 10 raised to power 4.5, or I can say root of 10 into 10 raised to power 4, right? It means basically roughly 3 into 10 raised to power 4, and the number of test cases are 3, sorry, 10 raised to power 3, so our time taken would be of the order 3 into 10 raised to power 7, and it will run within the time limit. And yeah, so this was it for this video, guys. Thank you very much.